Just like Black Pen Red Pen once said, yes, I am serious. So, hello and good day everyone. Good morning. Uh, Gandang umaga. Ohayo gozaimasu. Guten Morgen. Wherever on the world you may be, I wish you a pleasant morning. So, today, our agenda for today is that we'll be dealing with 25 chemistry and physics problems. And we'll be doing that in one take. Ayan. So these problems actually were taken from the supplementary problems on Simplified Engineering Thermodynamics by Chester Dilio. So I have the book right here for reference. And these problems are actually solved already by our professor in chemistry, and those were the problems regarding measurements involving basic physics and chemistry. So even though it has been solved before, I just want to reiterate some points from my perspective. So I have the paper with the solutions right here for the problems. Ayan. Ayan. So, and before I start this, before I start the problems, so I just have some people to acknowledge. Ayan. So, first of all, I want to dedicate this video to Idol Fiona and the rest of ME1103. So, ayan. Salamat sa sa Kasipagan Dust, Idol Fiona. And then, some special thanks to Miss Rosette M. Agbay. So, she's our professor in general chemistry. So, ayan. Even though we don't have a lot of things that we agree on, and I'm sure the rest of ME1101 to 1103 can relate. Even though there are some stuff, hanggang doon na natin sabihin. Looking on the bright side naman, she is a very passionate, very dedicated, very hardworking teacher. Napaka-dedicated sa craft niya. And we respect that. She's going out of her way to make lectures for us, and that is something to really acknowledge. Ayan. And then also wanna thank Engineer Jose Arvin Esther Dillo, of course, the author of this book. Ayan. So thank you for making engineering more simple. Ayan. And then I also got some shout outs. So first of all, my cousin Rowell, he's from ME1101, and kamusta na? As well as Robin from ME1102. Ayan, mga tropa. Also, I want to give some shout outs to my mom and my other 3 mother figures. So ayan. Yan. You know who you are na. And then I also have some special shout outs to CCs. Yan. My close friends Erica and Jovial. So even though nakakagigil kayo minsan, even though ganun, thank you for for being there when I need it. Ayan. When I need someone to talk to, and when I have some problems, I can talk to you both. So thank you, and I love you both. And then subscribe to Mr. Beast. Ayan. And just for the sake of this video, my medium of communication will just be on English and Tagalog, since if I speak in both languages, I can elaborate my points easier, even though I wanted to reach out a bigger audience. Sa tingin ko mas ma-explicate ko ang aking ideas if I also speak in Tagalog, or in Filipino rather. And enough introductions. Okay, let's move on to number 1. Okay, we'll start. Okay, so number 1. 2 cubic meters of water at room temperature has a weight of 19,600 newtons at a location where the gravity is equal to 9.80 meters per second squared. Find its specific weight and density at a location where gravity is 9.66 meters per second squared. So ayan, the first problem. So for these problems, uh, I, you don't need to do this on the test, but I will just elaborate that when doing your problems, you need to split it into parts. So you have your given, the asked, and then your solution, and your final answer. Generally, you want to split up your problem solving into these aspects. Okay, so first up, we will be starting with the given. Ayan. So what is our given? So we have 2 cubic meters of water. Yeah, 2 cubic meters of water. Okay, and then we also have 19,600 newtons. That is at 9.80 meters per second squared. If you notice on the problem, there are 2 units for gravity. Ano? So, gagawin natin, let's consider this as G1. This is gravity 1. Okay? G sub 1. Okay. And we also have this unit. Yan, ito yung second unit of the gravity as mentioned in the problem. And so, ito yung ating G2. Okay? Now, we have these parameters. Now, we will move on to what is asked in the problem. So, what is asked? The specific weight and density at 9.66 meters per second squared, which is our G2. Let's just say this is G2, so this is it. No. Yeah. Now that we know what is given and what is asked, we will move on to our solution. Ayan. Okay. So to compute this, first, we need to solve for the mass of water. And para magawa yan, we have our formula, which is mass is equal to weight over gravity. Okay? And it was derived from this formula, which is weight is equal to mass times gravity. Okay? In which you just divide both sides by g, so you get this derived formula. Okay, moving on. Okay, so the weight is as given 19,600 newtons over 9.80 meters per second squared. And one way to look at newtons is that this is the same as kilograms times meter per second squared. And now we cancel this, okay, and we are left with kilograms. Ayan. And then you put this in your calculator, and you will have 2,000 kilograms. So this is the mass rather of water. Ayan. And now that we have this unit, now we will look for the weight of water at G2. And now, like I said, The weight it is a vector, okay? It is influenced by gravity and has direction, unlike mass, which is a scalar. So weight is equal to mass times the gravity. Now we put in the mass. We have 2,000 kilograms multiplied to G2. G2 is 9.66 meters per second squared. And when you multiply this, you will have the unit Newton. Okay? So you input this in your calculator and your answer should be 19,320 newtons. Now that we have this parameter, okay, we move on to the next. We will now be looking for the specific weight. Okay. Specific weight Y. Okay. Y is equal to weight over volume. Okay, that is the formula. And now we input our values. So the weight earlier was 19,320 newtons. Ayan. At dito naman sa volume, tingnan natin itong volume. Here's the volume. Ayan. Okay. 2 cubic meters of water. Okay, this is in newtons. And when you divide that, we will end up with 9,660 newtons per cubic meter. And that is the unit for specific weight. Okay, newtons per cubic meter. Okay, so this is our specific weight right here. Let's just box this. Alright. And now we will be looking for the density. Okay, to solve for the density, so that is rho. Okay, this is not P, this is rho. The Greek letter rho. The density is equal to mass over volume. Okay. And that is equal to, like we have said, the mass of water is this 2,000 kilograms over, again, the volume is 2 cubic meters, and you input that in your calculator and our answer is 1,000 kilograms per cubic meter, and that is the unit for density. Okay, and let's just box this. Then I don't think I have space for the final answer, but the final answer is that the specific weight and density of water at 9.66 meters per second squared is 9,660 newtons per cubic meter and 1,000 kilograms per cubic meter respectively. And we are done. Okay, that is number 1. Okay, next, number 2. Determine the pressure of the water in the pipe if the water seeks a height of 10 feet. Okay, let me just look at my solutions here. Okay. Ayan. So, let's determine our given. So, we have 10 feet, which is the height. Okay, and then let's review that later on, and we move on to our asked. Okay, what is asked? It is the pressure of H2O in the pipe. Ayan. And now we move on to our solution. We'll still go back to our given in a bit. Okay. So to solve for the pressure, we have the formula, which is the, I think this is the specific weight, and then this is the height. Okay, so we have the height. Now what we need to consider is the specific weight of water. Hold on, if let me review if I'm right. I don't want to be making assumptions here. Okay. But this is the unit in this specific problem, so the Y of water is equal to, this is a constant by the way, this is 62.4 pound per cubic feet. This is a constant by the way. This is a constant. Right? Okay. Now, why do we decide with this unit? Because this unit is feet, and we can do some cancelling with that later on. Let me see if I am right. This is actually the yeah, it's the weight density. Okay, let me correct myself. It is the weight density of water. Okay. Now we input our units. So 62.4 pound per cubic feet times the height 10 feet, and we can do some nice cancelling here. This cancels 2, this reduces to 2, and this cancels, and you are left with 624 pound per square feet, and we can still convert that into another unit. Hold on. Okay. And so the unit conversion, we can convert this into we can convert this pound per square feet into pound per square inch. Pound force per square inch, or the PSI. Ayan. And to do that, we can multiply this by, hold on. So this is the unit. This is kind of excruciating to do, but it's 0.0069 hold on, 69, 4, 4, 4, and that goes on, over, that is just 1 pound per, this is, by the way, this is PSI, by the way, okay, just pound for cube, square feet, and then, hold on, this cancels, and you input that in your calculator and you will end up with approximately 4.33 psi. And another way to look at this is that 1 foot of H2O is equal to 0.433 psi. And you see here, so what you can just do is multiply this by 10, and we will arrive at the same answer, 4.33 psi. So it's a matter of unit conversion, okay, and this is approximately, by the way. And we are done. So for our final answer, the pressure of H2O, of the pressure of water in the pipe, is approximately 4.33 psi. So this is an answer as well. Okay. This is one way to look at the problem. Okay, moving on. Number 3. Okay, a 15 kilogram body falls from the rest, assuming no friction. Determine its velocity after it falls 10 meters. Okay. So, in physics, this is more of a physics problem. So para dito, it's important na ma-visualize natin kung ano ba yung nangyayari. Okay? So, a 15 kilogram body falls from the rest. Okay? So, we are assuming free fall. Okay? Let's say that this is a cliff. Okay, that's a bad looking cliff. Okay. Ayan. And then, let's say this body was a ball, a 15 kilogram ball. And this real estate are given here. It's better if we illustrate some of the problems in physics. So this is 15 kilograms. And it falls from rest with no friction whatsoever. And after it falls, let's say 10 meters, we just write given and asked, since we're gonna put our asked here as well. And after it falls 10 meters, what is the velocity after it falls 10 meters? Okay, so it started from this and it fell for 10 meters, and now we are looking for its velocity. Ayan. Then, as our given, we have 15 kilograms, 10 meters, and of course, if you are pursuing anything related into physics, engineering, chemistry, you have to know that the gravitational constant is equal to 9.81 meters per second squared. Okay? Now, we move on to our solution. Now, we must consider the conservation of energy. Okay? Conservation of energy. Ano? Which we can illustrate as E1 is equal to E2. Okay? And for this formula regarding velocity, we have the formula 1/2 meter times the velocity squared plus the mass times the gravity times the height. Okay, let me rewrite that. Okay, but in this case, we are dealing with this problem where we are trying to conserve the energy. So we have the initial velocity and the initial height, which is equal to the final velocity and the final height. Okay, let's just put another 2 here. Ayan. Where V1 is equal to 0. Diba? Saan ba yan? And let's just put this at 0 meters per second since that's velocity. And h1 minus h2, so the change in height is equal to 10 meters. Ano? Okay, so we can look at this from this perspective, that the mass times the gravity times h1 minus h2 is equal to the 1/2 of the mass times velocity. Ano? In which this is E1 and this is E2. So that's a little bit of analysis for that. And this, yan, marami talagang analysis. And this can be thought of V squared is equal to U squared plus 2GH. So this is another formula in physics that we want to consider when computing for the velocity of a moving object, where U is the initial velocity or the V1. Ano? Now we use this formula. Okay. So our initial velocity is 0. 0 squared plus 2 times the gravity, 9.81 meters per second squared, times the height, 10 meters. Okay. Then this actually has a unit, so para mas ma-analyze natin, so we can cancel it. This is 0 squared meters per second. Okay. So, see what we can cancel here. Reduce. This just turns to S. And then we just cancel this. Okay. So, we're left with V squared. Okay. Consider that V squared. Okay. V squared is equal to, if you put this in your calculator, you will end up with 196.2 meters per second. Now, to get rid of this exponent, this power, what we just have to do is simply take the square root of both sides. So this cancels, and we take the square root of this. So V is equal to the square root of that. That is 14.00714104 meters per second. Okay, and we can just round that off, so we can say that the velocity is approximately 14 meters per second. And we are done. Ayan. So we can say that from 0 meters per second, when it fell, when it started falling, and then when it reached 10 meters, it had a velocity of approximately 14 meters per second. Ayan. Ayan. Okay? Kakaintindihan. Okay, so that's the solution for that. Okay, we move on to number 4. Okay. A 15 centimeter diameter piston was uniformly applied by a force of 1,200 newtons. Find the pressure on the piston. Okay. We look at the given. The 15 centimeter diameter that was emphasized. Okay. Okay, so 1 centimeter diameter of a piston, and we have 1,200 newtons. Okay, which is the force applied on the piston, and we are looking for, our asked is the pressure on the piston. We have our solution. Okay, so we know in these kinds of problems, we know that pressure is equal to force over area. Okay, and for this specific problem, you have to let's recall actually the area of a circle is equal to pi r squared. Ayan. Ayan. In which we can explain this as the radius times the radius times pi, just 3.1416 and so on. Okay, therefore we can look at the area of a circle as the diameter times the diameter times pi 3.1416 and so on divided by 4. So why is there a why did we divide it by 4? So you note that uh, the diameter of a circle is twice its radius. So basically, we're taking 2 of the radius. Ano? 2 of the radius. And we're doing that 2 times since this is the diameter. So, supposedly, this was supposed to be over 2. You see the pattern here. That's supposedly over 2. No. Now, when we do it by the diameter, we divide it by 4 since the diameter is twice the radius. So that's the kind of explanation that I can make. So, ito. The area can be equal to pi over 4 times the diameter squared. No. And we'll be seeing that in this problem. Okay. Now, we compute. Okay. This is equal to the force is 1200 newtons. Then we input the formula here. Okay. So it's pi over 4 times, this is 15 centimeters, so we convert that into meters. 15 centimeters is 0.15 meters, and we square that. Now you input that in your calculator. Okay. So that is equal to 67,906.10905 newtons per squared. And this is the unit for Pascal. Yeah. And let's just convert that into another, let's make it smaller, the unit smaller. So you convert this into kilopascals. Okay, so 1 kilopascal, hold on, km squared you just cancel the unit, and that is equal to approximately 67.9. Let's just put it in kPa, kilopascals. Excuse me. Therefore, the pressure on the piston is approximately 67.9 kilopascals, and we are done. So just to give you a bit of an insight on how this happened, if you still don't get it, let's say we have a circle. I'm just clearing things up before we move on. So the diameter of the circle is this, and the radius of the circle is half of the circle. So any point from the center going into half. Yeah. So this can be the radius, and everything that starts from the center then going half. the radius of 15 centimeters is divided by 2, 7.5. This is the R. And the diameter is 15 centimeters. And you just convert it into meters later. So basically, the concept is that if you take twice of the radius, you're ending up with the diameter. Ano? Since it's the same concept as this. Ano? That is the radius. And if you take the diameter twice, then basically you need to divide pi by 4. No. So that's the basic concept of that. Okay, look at this. Okay. Since I think the area of the diameter of the circle is 2 times the radius, and since that is the that is the radius of the circle, this is basically the diameter. This ends up to the diameter, and when you take 2 of these, this is the same as saying that you are multiplying the diameter twice, and you just hold on to the unit. No. So if it's diameter times the diameter, you take this coefficients and you multiply and put it here under pi. So that's the best I can explain, since I'll be honest, I mostly forgot all of this already for the past 1 or 2 months that I have solved this. I've only done a video in here right now. So ayan, basta ganun yung concept na. And we are done. Okay, that's the solution. We move on. Ayan. Okay, number 5. A glass tube contains an oil of specific gravity of 0.85 to a depth of 150 centimeters. Find the gauge pressure at this depth. So again, let us visualize. So we have a glass tube. Okay, just forgive me for my humble drawing skills. It contains an oil. Okay, doesn't really matter what the height of the oil is. To a depth, it has a specific gravity. Specific gravity of 0.85 at a depth is at the depth of 150 centimeters. Ano? And we just convert this into meters. Let's just convert it to meters. This is 1.5 meters. Ano? This is the given. This is basically the given and the asked. And what we are tasked to find is the gauge pressure at this depth. The pressure. No. So let's denote this as our given and the asked. Okay. Solution. Okay, so we know that to compute for the pressure, we multiply the weight density times the height. Okay. But this time, since we don't have the weight density, we will substitute the formula, since consider this weight density as equal to the pressure, yes, pressure times the gravity. Okay, so we can look at this from this perspective, that it is PGH. Okay, it's really noisy right now, where the specific gravity is equal to P over PW. PW is, I think, this is the pressure of the water, I think. Okay, where P is equal to 0.85. Okay, which is the PW. Ayan. And then finally we can compute for the pressure. Okay, yeah, I was right. PW is the density of the water. Okay, let's correct this. This is raw. My apologies. This is raw. Ayan. Okay. And this is raw as well. Okay. Even I make mistakes. Ayan. Okay. Now, we can look at this as pressure is equal to the specific gravity times the density times the gravity times the height. Okay, now let's just break this up into multiple parts para hindi makalito. G H, and then let's put a parenthesis here as well. Ayan. And then we substitute the units rather. So specific gravity 0.85. The density of water, that is 1000 kilograms per cubic meter, times the gravity 9.81 meters per second squared, times the height 1.5 meters. Now, considering all of these parameters give you an answer of if we decide to all of these equate into Pascal, since it is the unit, it's the pressure, or newtons per square meters. And then solving further, you input this in your calculator, and we will end up with 12,507. Is that right? Yeah. 7.75 pascals, or if you convert, or 12.5 kilopascals. Yeah. So again, the gauge pressure at a depth of 1.5 meters is approximately 12.5 kilopascals. And we are done. So the gauge pressure here is 0.5 kilopascals. Ayan. Okay, let me zoom out. Okay. Move on. Number 6. Okay. We are 1/5 of the way through. This is gonna take so long. Okay. For number 6. The pressure recorded in the condenser of a steam power plant is 720 millimeters of mercury vacuum. Find the absolute pressure in the condenser in pascals. The barometric reading is 760 millimeters of mercury. Ayan. Okay. Now, again, we look at this systematically. Okay, dito. Given. Sorry for the dog. It's just life. Yeah. 720 millimeters of mercury. Ano? That is the vacuum recorded in the condenser. No. And then 760 millimeters of mercury. That is the barometric reading. Now, what is asked? What is asked is the absolute pressure in the condenser. This absolute pressure in the condenser. Ayan. And for our solution, okay. So we have the P absolute pressure that is equal to the barometric reading. Let's set that as P bar. The barometric reading minus the vacuum recorded in the condenser. Let's just set this as P vac. Okay. Now subtract. That is 760 millimeters mercury minus 720 Hg. And that gives you 40 millimeters of mercury. Okay. Now we are asked to find the absolute pressure in the condenser in pascals. Ano? Now we convert this into pascals. So basically, to convert it into pascals, you have to note that 1 millimeter of mercury is equal to 133.4 newtons per square meter, which is pascals. So we do dimensional unit analysis. Okay, 33.4 pascals is 1 millimeter of mercury. Okay, and then we cancel, which gives us 5,000 rather, 336 pascals. And therefore, our final answer is the absolute pressure in the condenser is 5,336 pascals. So this is our P absolute. And we are done. Na. Okay. Okay, so far so good. Tama, if I'm still recording. Okay. Alright. Okay. Number 7. A barometer contains mercury with a density of 13,593 kilograms per cubic meter. Atmospheric conditions are 101.32 kilopascals and 20 degrees Celsius. At this temperature, the vapor pressure of the mercury is 0.000173 kilopascals. At what height will the mercury rise? Yan. This might sound complicated, but let's deal with this. Okay. We look at our given. We have 13,593 kilograms per cubic meter. This is the density of mercury. Okay. And then we have 101.32 kilopascals. What is that? Pascals. And then we have 0.000173 kilopascals. This is at 20 degrees Celsius. Okay. Now, so we do a little bit of deriving on this side. So let's look for what is asked first. The height. The height in which the column of mercury rises. Okay. Oops. Now, with your solution. Okay. Okay. For our solution, we have to consider this formula. Since we are given two pressures, so we have pressure A is equal to pressure B plus the density, I think, is it? Yeah, the density, or times the gravity times the height. Okay. Ano? Now we manipulate some of the variables here. Divide both sides by PG. Okay, let's just include this side. Okay. And then this cancels. So pressure A over the raw. Yeah, just consider that as consider na lang to as d raw. It's very similar to P, so that's pressure B plus the height. Now, how do we get rid of the pressure B? That's simple. Subtract both sides by PB. Okay? Minus PB. And then you cancel. Okay? Very good. Therefore, our height is equal to pressure A minus pressure B over density times the gravity. Okay? Okay, nakasunod. Alright, now we input our variables. Let's consider this as the pressure A and this as the pressure B. So, pressure A, okay, we put that with 1.32 kilopascals minus 0.000173 kilopascals, okay, over the density 13,930 kilograms per cubic meter times the gravity 9.81 meters per second squared. And then we want to convert this into pascals so we can do some canceling. So let's just add that here. So this will be let's just shortcut it, 1000 pascals over 1 kPa, and the rest of this cancels. Okay, let's just cancel this, and this, and we're left with pascals. Okay, now that we are left with pascals, that is newtons per squared. Okay, and and consider newtons. Okay, consider newtons as kilograms times meter per second squared. Okay, alright. Okay, yeah, medyo dugo yung analysis, but that's how chemistry is. Ayan. Now we can cancel kilograms, and then we cancel meter per second squared, and then finally reduce this to 1, and this cancels, so we're left with meters. Alright, and if you input this in your calculator, you will have an answer of 0.75981899405 meters, in which we can just approximate it into, hold on, okay, that our height is approximately 0.76 meters. Therefore, at approximately 0.76 meters, the column of mercury will rise. And we are done. Okay. Ayan. This is for number 7. Okay. Okay. Next. Number 8. Ayan. Ayan. Huh. Okay, this one is kind of easy. Okay. Density of the gas is 2.5 kilograms per cubic meter. What is the specific weight of the gas? Okay, I didn't know. I actually read it from before. I actually repeated myself. Okay, nevertheless, yung ating given, ayan, our given is 2.5 kilograms cubic per cubic meter. Okay, and what is asked is the specific weight of the gas. Hold on. Yeah. And we could look at this as the specific weight y. Hold on, let me write the solution. We can look at the specific weight y, ayan, is equal to take note of this, density times gravity. Okay, now we just apply the variables. 2.5 kilograms per cubic meter times 9.81 meters per second squared. Okay, ayan. And again, consider this. Yan, titingnan nyo ta. The unit of kilograms times meter per second squared. Does something seem familiar? Yes, that is the unit for newtons. So your answer will be you input this in your calculator and that unit. So that is 24.52 newtons per cubic meter. This is your y. And that is the specific weight. So therefore, the specific weight of the gas is 24.52 newtons per cubic meter. And we are done. Okay. Ayan. It's fairly easy. Next. Moving on. Number 9. A fluid has a density of 920 kilograms per cubic meter. What is the specific gravity of the fluid? Again, we're computing for specific gravity. Okay. There's the given. We have 920 kilograms per cubic meter. Okay. Asked specific gravity of the fluid. Okay. And we move to the solution. Okay. To compute for this specific gravity, okay, take note of this formula. That is the density of the fluid over the density of the water. Ayan. Ayan. So that is 920 kilograms per cubic meter over the density of water is 1000, and both of these units cancel since ang specific gravity ay walang unit. Take note, our specific gravity is 0.92. Ayan. Therefore, the specific gravity of the fluid is 0.92, and we are done. Okay, that's number 9. Move on to number 10. Ayan. Okay. A vessel is initially connected to a reservoir open to the atmosphere. The connecting valve is then closed and a vacuum of 54.9 kilopascals is supplied to the vessel. Assume standard atmosphere pressure. Determine the absolute pressure in the vessel. Ayan. Okay. So again, on these kinds of problems, it's nice that we are able to visualize. Okay? So let's say we have a vessel, and this vessel is connected to a reservoir. Let's say this is the reservoir, and let's say that's the reservoir, which is open to the atmosphere. So let's say that it has some kind of opening right here. Let's assume the connecting valve, let's say there's a valve right here. Yeah. Okay. Yeah. And forgive me for my humble art. It's more of a mushroom. Anyways, let's redo that. That was kind of pathetic. Let's try to do this. Yeah. No, it's more of a flat mushroom, but that looks more of a valve now. Okay. It was closed. Okay. It was closed, so it was rotated. Okay. It was rotated, and then a vacuum of 54.9 kilopascals. Okay. Let's say they applied a vacuum of 54.9 kilopascals after closing this valve. Okay, so this is basically our given. And let us ask the absolute pressure in the vessel. Okay. Okay. Now, let's do some analysis. In the problem, there was a statement that said that we are to assume the standard atmospheric pressure. However, okay, that is 1 atm. However, this unit is in kilopascals. This unit is in kilopascals. So, one ATM, that's a note. 1 ATM, that is equal to basically 325 kilopascals. Okay. This is just an easy problem, so we have the solution. okay, is that the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. This is basically the formula for this. Okay. Now we just simply substitute the units. Okay. So again, we do analysis here. Assume that a vacuum of 54.9 kPa is applied to the vessel. So I guess this would be negative. Ano? It was applied, however, ano ba tayo explain? It's somehow negative because it stayed there in the vessel, I guess, even though it was added. It was supposedly added to the vessel, but it's negative. Ano? Okay. So it's 101.325 kilopascals plus negative 54, is it right? 0.9 kilopascals. And you subtract that and you will be left with 46.425 kPa. So again, I think the reason why it was negative is that when the air was flowing from here to here and then into the atmosphere, it was suddenly cut off. Ano? And when they added the vacuum, it sucked out the remaining air here. So ibig sabihin, parang nawala na yung pinaka pressure inside the vessel since the valve was closed, and then you applied a vacuum. You sucked the air out. Ano? That is probably an analysis of how it was supposedly negative, but therefore the absolute pressure in the vessel is 46.425 kilopascals, and we are done. Hold on, let me add the absolute. Okay, I can do better than that. Hold on, just to clear confusion. Ano? Ayan. Okay, so even though it was an easy problem, you have to make thorough analysis, and that is engineering. Okay. Alright, we're on number 10. We're done with number 10. We move on to number 11. Yan. A 32 degrees Celsius water flows at 2 meters per second through a pipe that has an inside diameter of 25 millimeters. The viscosity of water is 820 times 10 to the negative 6th power Newton second per meter, and density of water is equal to 999 kilograms per cubic meter. Find the kinematic viscosity of water. Okay. Again, I'm not sure if I can visualize this. My skills in drawing is horrendous, so okay, let's try. Ito na lang. Let's add two circles here. No. Yeah. This will serve as the given. Ayan. And we basically connect these pipes together. Ano? And let's just say that here's a pipe here, and then ayan. Actually, that doesn't work. Anyways, let's say that this is a cross section of that. Okay. Now, there's water flowing in this pipe. Let's just stay. Ayan. This is cross sectional naman. And the inside diameter of this pipe is 25 millimeters. Is diameter. Okay. Ayan. Okay. And then now to visualize what's happening, to look for what is asked. Kinematic viscosity. Viscosity of the H2O. And take note, what is flowing here is this is water. And its density is this. And also we have the viscosity. Viscosity is denoted by this mu symbol, the Greek letter mu, which is equal to 120 times 10 to the negative 6 power Newton second per what's that? Meter squared. Okay. Ayan. Now, to simply do this, we didn't actually need to illustrate it anyways, but I did just because to visualize the problem, because all the variables here are hindi na naman natin kailangan lahat ng variables na nandito, diba? I'll tell you much later. So the solution is to find the kinematic viscosity V of water that is equal to the viscosity over the density. Okay? And that is 820 times 10 to the negative 6th power Newton meter second. I got the order wrong. Newton second per meter squared over 999 kilograms per cube. Considering that this is kilograms times meter per second squared. We can do some nice canceling over here. Okay. Okay. So kilogram cancels. The second, no. I think yes. Seconds will be with this reduced. And then second per meter squared. Yeah, right. Okay. Second will be reduced to 1. Okay. And then we end up with this unit. Anyways, it's m squared over seconds. I suppose we just cancel this, so it reduces. Cancel that, so it reduces. This is 1, and then this reduces to 2. Since this is a unit analysis anyways, and this is being divided anyways. Okay. So we are left with this unit. We're left with the unit meter squared per second. Okay, and that's the unit for kinematic viscosity. Therefore, you input this in your calculator, and the answer is 8.208208, and so on, times 10 to the negative 7th power meter squared per second. And okay, and you can just round that off. You can say that your V is approximately 8.21 times 10. To the negative 7 power. Yan. Meter squared per second, or if you want to bring it to the same unit as itong initial unit, ito, kung saan negative 6 yung iyong power, you can just convert that. That is 0.82 times 10 to the negative 6 power. Ayan. And we are done. You see? Kita nyo. We are given many units, although we only used the viscosity and the density. We are given this, but hindi naman natin siya ginamit. We're given this. We're given the temperature, and we're given the rate of flow, but we didn't use that. So we have to analyze the problem. We have to analyze what we're looking for to make sure that we can arrive at the right answer. So ayan. So therefore, the kinematic viscosity of water is approximately 0.82 times 10 to the negative 6 power meter squared per second. Square meter per second. And ayan. Okay. That is for number 11. Number 12. Ayan. A fluid with a vapor pressure of 0.4 pascals and a specific gravity of 14 is used in a barometer. The fluid's column height is 0.8 meters. Find the atmospheric pressure. Okay? Ayan. Okay. So we consider our given. I didn't know it was gonna be this tiring. Am I still recording, by the way? Okay. 130 minutes in, and we're almost halfway. Okay. So we're given 0.4 pascals, 0.8 meters, and 14, which is the specific gravity. This is the height, this is the pressure. Now, we look at what is asked. We're asked to find the atmospheric pressure, which we'll just denote as P ATM. Our solution. Okay. We can look at the atmospheric pressure as P ATM is equal to the P of A plus yes, the density times gravity times the height. Okay? And in this case, itong ating PA, that is the vapor pressure. Okay? So pressure, vapor pressure plus, now we are not given the density. So we can look at this as the specific gravity times times the density of water. Okay? Ayan. So we input that. Specific gravity times density of water times gravity times height, and we input our values. 0.4 pascals is the vapor pressure plus specific gravity 14, density of water 1000 kilograms per cubic meter, gravity 9.81 meters per second squared. The height is 0.8 meters, and we note that all of this is just equal to Pascal. And you input this in the calculator, and you will end up with 109,872 pascals. And we convert this into kilopascals, so we divide this by just 1000. Let's do this here. Pascals and 1 and we just cancel the units. So we can say that the atmospheric pressure is equal to, let's just approximate this. This is approximately 110 kilopascals. Same with this. 110 kilopascals. Okay, and we are done. Okay. So therefore, the atmospheric pressure is approximately 110 kilopascals. That's it. Next, number 13. A condenser vacuum gauge reads 580 millimeters mercury when the barometer reads 760 millimeters of mercury. Determine the absolute pressure in bars and kilopascals. Okay. It's kilonewtons per meter squared, which is basically kilopascals. Okay. Now, let's look for the given. We are given 580 millimeters of mercury. That is the gauge pressure. Then we are given 760 millimeters of mercury, which is the atmospheric pressure. And we are asked to find the absolute pressure in bars and kilonewtons per yes. So take note of this. Now, just find the solution. So to find the absolute pressure, it's just equal to the atmospheric pressure plus the gauge pressure. Now, look at the problem again. A condenser vacuum gauge reads 580 millimeters of mercury. So when a gas is in a condenser, it basically reduces the energy of the gas. Since it's undergoing the process of condensation, in which the gas is being turned into a liquid. Therefore, the pressure is negative. This is negative. Ayan. So, that is equal to 760 millimeters mercury plus negative 580 millimeters of mercury, and that is equal to 180 millimeters mercury. Now we just convert this into bars and into kilonewtons per meter square meters. You can do that. So 180 millimeters of mercury. I think we should do this here. Hold on. We can do better than that. Kita. Para maraming space. Ayan. So, 180 millimeters mercury. Ayan. Take note that for every 760 millimeters of mercury, there is 101.325 kilopascals. Okay. and then we just cancel these units. Okay, and we are given the answer. You just input that in your calculator. Let me just check, since I've been doing this on intuition until now. Okay, that is equal to 23.9980, and it goes on. So that's approximately 24 kilopascals, which is the same as kilonewtons per square meters. Now this is your answer. Hold on. This is your answer in kilonewtons per square meters. Then we convert it again, this time into bars. Now take note that for 1 bar there is 100 kilopascals. And now we cancel the units, and we are given with, again, this is equal to 0.240 bars. Just approximated it, since the answer would be something like 0.23999. Yeah, we just approximated it. And so this is our answers in bars and in kilopascals, and we are done. Okay. So the final answer is the absolute pressure is 24 kilopascals and or 0.240 bar. Okay, we are past halfway now. Very good. There are 12 problems left. Okay, for number 14, calculate the A, height of millimeters of mercury column in a barometer placed on a mountain with a local pressure of 12.9 psi, or pound force square inch, I think. And then the equivalent pressure gauge of a compound gauge measuring a pressure of 25.3 rather in mercury. Hold on. Hold on. I'll just check if what I'm saying is right. Yeah, pounds per square inch is psi. Okay. Let's just go straight to the solutions, because there are 2 things we need to solve, and the page won't suffice if I did that. Okay. Okay. For A, okay. For letter A, so we're calculating for the height. Height is equal to the Wait, hold on. 12.9 psi. Yes, 12.9 psi, which is pound per square inch. Okay. Wait, let's actually just do the variables first. It will be confusing. So it's the pressure over the density. And since we're not given the density, we can express this as the specific gravity times the density of water. If I'm correct. Hold on. I think the solution I did was not full. It was yeah, density of water. And we know that since the element is mercury, take note. Hold on. Note. Sg of mercury is equal to 13.6. Take note of that. And you have to convert this into a factor that we can cancel the units in. So I guess we have to convert the pressure into something that we can cancel. Okay, so we have 12.9 pounds per square inch. Now we convert this into hold on, maybe I got the order wrong. It's nice that I got the book here for reference in case I made a mistake. It was just here. Calculate. Calculate. What's the problem here? Yeah. It's here. Okay. Was it above the thing? Hold on. Okay, so supposedly, sorry for that interruption. Supposedly, let me set it up. I'm supposed to convert it into feet. But shouldn't it be something like this? I will try converting just to check, since I don't want to give a wrong answer. 8.9 Yeah, yeah, yeah. Yeah, I was just converting it into feet. Okay, okay, okay. I got it. So we have to convert it in terms of feet. Okay. So for every feet squared, there is 144 square inches. And this is just an analysis. This is not interfering with the original equation. Okay. And then you have the specific gravity of Mercury, 13.6, times the density of water, but in terms of pound feet. So it's 62.4 pound per cubic feet. Okay. Alright. And then we can do some nice cancelling here. This and this cancels. So the one was I was wondering about, since you get to cancel this, but this is in the numerator. Maybe this is just how it is. And then we cancel this, and this reduces to 1. Okay. And you input that in your calculator, and you will be left with a nice 2.1889 feet. Okay, in which we want to convert in back into um, millimeters. Okay. To convert this, we have to convert it into meters first, and for every 1 meter there is 3.28 feet. Okay, we cancel, and before we arrive at the final answer, we have to convert it back into millimeters. So for every 10,000 millimeters there is 1 meter, and we cancel the units yet again, and you input this in the calculator, and you should have the answer of 667.35 millimeters. That is the height. Okay. This is the height of the mercury column, and we're done with A. Okay, now we still have space for B. I think that is not as long as A, so we solve for B. Solution. Now for this part, we will have to find the equivalent pressure gauge of a compound gauge measuring a pressure of 25.3 in Hg. Okay. Okay. That is, yeah, it is P gauge, which is equal to, I think this is the density again times H times the height. Okay. Okay. Was it really? I know it's 13.6, but it's stated here that the unit for the specific gravity of Mercury is 13.55. Let me try to find the reference in the book. Hold on. Yeah. What's it 13.55 but it's 13.6 here? So I'll just adapt. I'll just use the unit, which is 13.6. Yeah. Because we don't want to deviate that much. So, we do this. The density is again specific gravity times the raw of water, density of water. Now, specific gravity is again 13.6 times. Again, we have to look at the density of water in terms of pounds and feet. Okay, 62.4 pound per feet cube. Yan. Okay, yan. Tapos, split it in brackets. We still have space. Okay. We multiply that by the height, 55.3 inches, and then converting it into feet cube. Okay, to feet cube, to cancel this out. Okay, and that is for every 1 foot cube there is 1728 cubic inches. Okay, now we can do some nice canceling. Okay, we can cancel feet, cubic feet, and we can reduce this into 2. So our unit will be in PSI, pound per square inch. Okay, and you now put this in your calculator quite nicely, and then you will end up with, however I have changed the value from 13.55 into 13.6, so the value probably has changed, so I'll calculate it from scratch. It's 2.4 times, okay, we have 25.3 divided by 128, and we end up with 12.425111, and that goes on. PSI, pound per square inches, and we can round that off quite nicely into 12.43 pound per square inches for PSI. That is the P gauge, and we are done. Okay, ayan, medyo madugo tong number 14 na. Okay, it gets easier. Okay, am I still recording? Yes, we're 2 hours now. Wow, okay. Number 15. 11 problems. Okay. Convert vacuum pressure of 110 millimeters of mercury into absolute pressure in meters of water if the atmospheric pressure is 10.33 meters of water and specific gravity of mercury is 13.6. Okay, let's just do this quite nicely. Given 10 millimeters of mercury. I think the vacuum pressure is the atmospheric pressure, if I am correct. Since on the other problem, I said it was PVAC. It was PATM. I stand corrected. 10.33 meters of H2O. And we have 13.6, which is the SG of Hg. So that's our given. And we are asked to convert vacuum pressure. Let's just say it was PATM. Hold on. Before I make any more mistakes again. Pressure of yes. 40 meters or atmospheres. Let's just to be safe. Let's just say that it's P vacuum. P vacuum. Do what? What are we converting to? Absolute pressure. Okay. So to compute for that, again we're using this formula where the absolute pressure is equal to P atmosphere plus the gauge pressure, P gauge. Okay. Is this though? So suppose we will, it was stated as PG, so I don't know if it was gauge or something, but first we solve for PG since we don't know that amount, and we can take this from here. Okay. So we can solve for this, where PG is equal to, I think it was the negative specific gravity times millimeters of mercury and the density of water. Yeah. How do I solve for this though? Sorry, don't remember. I just want to clear out. Yeah. Looking for height. How will it come to be then? So this is the negative specific gravity times going to P vacuum. Yeah, P vacuum. Yeah, I was right. It was not the same as the atmospheric pressure. I'm sorry for that. Over. Where did I get the amount of 1000? Did I convert it into meters? I think I did. I think I did. Did convert it to meters. So this is basically just a matter of unit conversion. P vacuum. That is equal to negative 13.6 times 110. Yeah. Negative 13.6 times 110 is negative 6. That's 1.96. And then as our supposed units are meters of water. I don't know the unit analysis for that, but we divide this by 1000. This is this is millimeters. Okay. And this is 1 meter over 1000 millimeters. Simply cancel these units. Try for that. And then we are left with negative 1.496 meters now of water. That is the analysis. And then that is basically PG. Okay, and we can substitute the values finally. 10.33, that is meters of water, plus negative 1.496 meters of water. Okay. You put that in the calculator and you will have the answer of 8.834 meters. Yeah. Okay, so this is the absolute pressure in terms of meters in water. So therefore 110 millimeters of mercury is converted to 8.834 meters of water, and we are done. Okay? Okay? And now, number 16. And now this is fairly easy. The temperature of a solution is 28 degrees Celsius. Convert this temperature to absolute Fahrenheit, which is degrees Rankine. Okay. So we are given 28 degrees Celsius. We are asked to convert to Rankine, degrees Rankine. And for our solution, we will have a process of solution where we will convert degrees Celsius into degrees Fahrenheit and into absolute Fahrenheit, which is the degree Rankine. Okay. So, to convert this into Fahrenheit, so degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32. Okay, and we just put in the value. I'll just put it here to save space. Never mind. Over 5. We put in this value here. 28 degrees Celsius plus 32. We put this in the calculator. You will end up with 82.4 degrees Fahrenheit. Okay, now to convert this into degrees Rankine, that is basically the degrees Fahrenheit plus 460, and that is 82.4 degrees Fahrenheit plus 460, and you just simply add this and you will have an answer of 542.4 degrees Rankine. And we are done. So the final answer is 28 degrees Celsius is equivalent to 542.4 Rankine. Okay. So the temperature of the 28 degrees Celsius solution is equivalent to 542.4 Rankine, degrees Rankine. Okay. So this was number 17. Okay. Determine the pressure, kPa, of metal structure at the bottom of a brine. The brine is the salt solution tank, 2.42 meters deep. The specific gravity of brine equals 1.03. So this is similar to the other problems earlier. Okay, so take a given. We're given the height, 2.42 meters, and the specific gravity, 1.2. The specific gravity, ayan. And we are asked to find the pressure. Okay. And for our solution, that is just the pressure is equal to the density times the height of the structure. Yeah. Okay. And again, the density is absent from the problem, so we can consider this as the specific gravity times the density of water. Okay, you see the similarity? And now, uh-huh, hold on. Huh. I'll be looking at the book again. Oh, I see. Because we're looking at this from the perspective of meters. Wait a minute. Just want to find. We have to make it appear in kVA. What is the unit that can do that? It doesn't make sense. We substituted gravity 9.81, but it does not make it to the kilonewtons per square meters. Hold on. Okay. What's it 9.81? I don't get it. If it was something that can be converted into newtons, there's none though. If I did the unit for density, it would not be suffice. So I guess what they did here was use gravity as a substitute for the density of water. So that's what they did. So we have 1.03 times 9.81. I don't get how this would work though. 1.81 times 2.42. So even though I'm still not clear of how this works yet, but it somehow equates into kVA because it says in the book. Okay. I guess that is a shortcut since we're looking for kVA times 2.42. I won't go into this much further. Oh, my stomach is acting up. It's already 1 p.m. and I haven't taken lunch. Let's just wrap this up. Okay. So it's 1.03 times 9.81 times 2.42. I guess it is a shortcut to find the pressure. I can't seem to wrap my head around this, but the answer is 24.45 kilopascals. Maybe there's another solution by ma'am that we didn't analyze it much. It was months ago. Hindi ko naalala kung ba't naging ganun yun. But somehow this is the answer. Somehow. 24.45 kPa is the answer. Okay? Or maybe ma'am had a different take for this. You guys can look for it. But for now, this was my answer for this problem. Okay. So basically, the pressure is 24.45 kilopascals. And that's it. We are done. Okay. I'm still not sure about this though, so you guys can argue with this or just skip this part. Okay. All right. Uh-huh. Density of water is typically taken as 62.4 pound mass per cubic feet and 1000 kilograms per cubic. Is that pound meter? Yeah, pound meter. For engineering problems where greater accuracy is not required, what is the value in A, slugs per cubic feet, and B, kilograms per cubic meter? It's a matter of derivation. Hmm. Mm-hmm. Okay. 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 How to find the given? Huh. Actually, no. We just do the conversion factor. So we look for A first, which is the slug density of H2O. Okay, so rho is equal to okay, remember this formula, so it's 62.4. Hold on, it's a matter of conversion. Yeah. You don't need to put the variables in. Pound mass per cubic. Is it pound meter? Yeah. Pound mass or pound meter? Pound mass, yeah, per cubic feet. Okay, yeah. Oh, we can do that later. And this is over 32.2 pound mass as feet over LBF. What's LBF again? Let me see. So hold on. pound force. Pound force second squared. Okay. So we can just do some nice canceling here. This cancels and this cancels, and you reduce. If you reduce this too, and then cancel this out. Yeah. This is load. Yep. 1 feet. Yep. Yep. Yeah, it's a given. It's a constant. It's constant. We're just deriving it. I was confused. So that was 1.94. 94 pound force a second squared over feet. You're wondering why this. Actually, no, this was wrong. I think we just retain this formula here. Yeah, this retains because it's slugs per feet per cubic feet. Yeah. That's the analysis. This is the unit for slugs. So it's basically 1.94 slugs per cubic feet. And this is the answer for this. It's a unit conversion. You can look it up. It's just a constant. But this is a solution for it, or what it says in the book otherwise. And lecture B. Is the value of value A rather kilograms per cubic meters. Okay. Yeah. Yeah. Okay. Density is equal to, we use the given 62.4 pound mass per cubic foot times. Now we're using conversion factors again, which is, because I think for every meter per cubic feet, which is 35.31 feet cube over meter cube over 2.205. We're converting mass for pound mass per kilogram. Put it in the parentheses. Okay. Yep. And then first we do the operations here, so we can cross multiply the units. Just a 2.4 pound mass per cubic foot times, divide that will give you 16.1. Now I think what they did was cross multiply the units, like something like this. So it's cubic feet foot times pound mass kg. Yeah, I think they cross multiplied here and then here. Good. So the unit is kg feet cube over cube minus pound mass. And you see this? You can do some nice cancelling. Oh my god. Okay. Cancel pound mass. Okay. And cubic feet. And you do the operations here, and you're left with 199 kilograms per cubic meter. You can just approximate that into 1000. That is the density of water in kilograms per cubic meter. And we are done. Oof. Oh my god. Okay. Miss something? Yes. We're supposed to have cross multiplied the units. Here. Yes. Again. I think that's what we're supposed to do, because it was shown here that it had feet, right? Or something like that. It was just a conversion factor. There's no need to make the formula even worse. Okay, number 19. Whew. How much time am I recording? 2 hours 34 minutes. Okay, I think I'm still audible. Okay. Determine the sea level specific weights of liquids in pound force per cubic feet having densities of A 1.75 slug per feet. I think it has this. Yeah, I missed the thing. Yeah. Cubic feet. And B 62.6 pound mass per feet cubic. Add that with gravity equals 32.2 feet per second squared. Okay. Now this is more tiring than I expected it to be. Okay. Go to A. So specific weight y, hold on, specific weight y is equal to the gravity times the density. Yep, yeah, the density. And then we just apply the principle. 32.2 feet per second squared times 1.75 slugs per cubic feet, which is the same as squared over, yeah, yep, yeah. And going back to this problem, actually I was right on this. It was the unit. You don't cancel this unit out. Since you multiply it instead of cancelling. So this is feet cube. Okay? And we can do some nice cancelling. Cancel feet. And second squared. Okay. Yeah, we're looking for the pound force per cubic feet, and we have it. You put this in the calculator and you will have 56.35 pound force per cubic feet. Then for letter B, this is the for the first one. This is the specific weight. Okay. Alright. And then for letter B, we use the same formula basically. So specific weight, yeah, let's just clear things up. Two, 2.2 feet per second squared. Okay. Gravity times this. Now, if you look here, I think you'd have to divide it by the slugs. Yeah. LBM feet, pound force second squared. Yeah. So that will be equal to the gravity times the density over, I think this is, hold on, OBM feet. Mhm. Pound force. Uh, it's newtons, though. Hmm. Okay. And we can denote that as G of C. Okay. G of C. Yeah. We can denote that as that. So in the solution there is 32.2 feet per second squared times the density 3.6 cubic feet over 32.2. This is, I think this is a constant, yeah. LBM feet over pound force per second squared. I think the reason you're dividing by this, since uh, this is the same, no, it's the same unit, so we can cancel units out, yeah, because we're trying to reach this. Okay, so we can do some nice canceling, yeah. It's up to us to manipulate the variables. Cancel this, cancel that, and then cancel this, that, this, and that, and we're left with, you perform the operation on the calculator, and of course, yeah, it's gonna be 2.6 pound force per cubic feet. That will be the specific weight. And we are done. Okay. Yeah. Still have to wrap my head around this other units and slugs. Yeah. That's it for number 19, and then we can add any more frames, so we move on to the next part. Okay. We have 6 problems left. And how long am I recording now? Almost 3 hours. Wow. Okay. Okay. Before that, actually, I'll just grab a little snack, since I don't know if I can continue. That is dizzy. I'll be back in a bit. I think I'm still recording. Hold on. Before we move on to the next problem, actually. Man. No, that's fine. Okay. I'll just show it towards the end. Okay, number 20. 120 grams of water is mixed with 200 grams of another fluid with a density of 140 kilograms per cubic meter. Determine the specific gravity and specific volume of the resulting mixture, assuming the volumes are additive and the mixture is homogeneous. So when we say that the volumes are additive and the mixture is homogeneous, basically you can just add the volumes together. So we can see here, okay, of the given 120 grams of H2O and then 200 grams of another fluid with a density of 940 kilograms per cubic meter. We're asked to find the specific gravity and the volume. Now for the solution, yeah, since they're additive, we have to add the volumes of these liquids and their specific gravity. Ano? So water, specific gravity of water is 1, and the specific gravity of this is just the density of fluid, fluid over density of water, which is 940 1000. This is both kilograms per cubic meter. Okay, and cancel, and it's a ratio, so it has no units. That is equal to 0.94. Now to add the volume, it's just it's the device a formula, since I have the direct solution here on the paper. Okay. Yeah, let's just set it as the mass. Yeah. Mass of H2O over the density of H2O plus, it's additive, okay, fluid, density of fluid. No, this is SG actually. The SG of the fluid, specific gravity. Okay, Then this is the density of the mixture. Okay, okay, alright. Mass of H2O 120. Specific gravity 1 plus 200 over, yeah, this is the mass of the fluid, and then the specific gravity is 0.940. Now take your calculator. Hold on, it's a little different than what I expected it to be. Must be something that we manipulate here even more. Oh, oh, wait. 12. Yeah, since it's additive. Two point nine four zero. Wait, it's not right. Hold on. Let's try the discrepancy here. Yeah, where is that arriving at? 0.962. Oh, hold on. You can look at this from this point. As the wait, dito 200 plus 120 is the density of the mixture over the density of the mixture. So it's just actually 1 divided by huh? Hold on, I'll be reviewing this. Oh, oh, huh. We convert that into centimeters. Is that it? Okay. Hold on. It's the answer here. Nine five seven four. Yeah. Hold on. It's centimeters. Centimeters. How do they even arrive at that answer, though? Oh no. Yeah, I think. Hold on. Alright. I think I may have got the thing. Okay. I'll take this first. This is the volume. Yeah, I mistook it for the density of the mixture. Okay, that was not it. So we just take this. You take that and you're given this. Hold on. Plus here. This is your 2 7 6 5 1 5 7 4. It was actually density because we just converted it into grams per cube. And then this is grams and this is grams, so this will cancel. This will both cancel. And this is the unit. Okay. And test that out. We have yep. Alright. Yes, I got it. What am I thinking? The density. We have the volume now. Now that we have the volume, I was just copying from the book. This is the volume, and then this is it. This is the volume. This is one answer down. Okay. Apologize for that. And we use this to calculate for the density. Yeah, that was it. Yeah. And we all know that the density formula is just the mass over the volume. For the mass, you combine this 20 grams over this 2.7659574 cubic centimeters. Okay. And you will lead to the answer of 0.961636 and so on. You just round it off into 0.962 grams per cubic centimeter. And we use this value to calculate for the specific gravity. We just divide this into the the density of the fluid is I got it. We will use the formula here. Am I still recording though, by the way? Will be alright. 2 hours in. Man, this is some torture, bro. Okay. So we're calculating for the specific gravity, which is now the density of the mixture over density of the water. Alright, just continue that over here. Density of the mixture is 0.962 over 1. Okay, so there we go. We just cancel this and we will just approximate it. Actually, this is now equal to approximately 0.96, and we are done. Whew, that was, oh my god, oh my god. Ooh. Okay. So the volume is 332 point. We can just round that off. Actually, let's round that off. Since you don't really want a big answer. Volume is approximately 332.77 grams per cubic centimeter. And you got it. Okay, there we go. So the volume is approximately 332.77 grams per cubic centimeter, and the specific gravity is 0.96. Okay. Whew. This is tiring. Okay, 5 more problems to go. Okay. Oh my god. Okay. Now, number 21. Oil with a specific gravity of 0.97 is used as the indicator in a manometer. If the differential pressure across the ends of the manometer is 8 kilopascals, determine the difference in oil levels in the manometers. Okay. For this problem, you're given the SG of the oil, which is 0.97, as well as the pressure 8 kPa. Okay. Okay. And we are asked to find the difference in oil levels. In oil levels. We take note of this. Levels. That could refer to the height. Okay? For the solution, so we compute for the density of oil first. Okay? Yep. Density of oil is now equal to the specific gravity times the density of water, and that is 0.97 times 1000 kilograms per cubic meter. It's just 170 kilograms per cubic meter. Now we take this value. Okay. And we can be sure that to compute for the pressure, or at this time the change in pressure is just set at the delta P, that is equal to PGH. Yeah, the density, the gravity, and the height. However, we're looking for the height. So what do? We just divide both sides by rho and g. Okay, and we have a new formula, which is the height equal to delta P over rho times g. Okay. Now, since we are trying to make this a lot more simpler, we can convert 8 kilopascals into pascals, and we just simply multiply this by 1000. So if you want to see how that works, let's just do it. So 1000 pascals over 1 kPa, and we cancel the units. We will have 8000 pascals, and take note of this later on. So now we solve for this. Let's do it here. Let's do it here. Okay. There. So the height is equal to 8000. Now pascals is the same as newtons per meter squared. I've said this many times. Over the density is 970 kilograms per cubic meter, and of course gravitational constant 9.81 meter per second squared. Now, how do we make it so that it only has meters? It's just easy, bro. So ganito. Why am I talking so casually now? Ayan. So I'm kind of tired. Ayan. The fatigue is getting up to me. So newtons is the same as kilograms times meter per second squared, and we cancel. cancel kilograms. We can cancel this, reduce this to 1, and we cancel meter per second squared, and we're left with meters. So you put this in the calculator and you will end up with, I think I just approximate the answer here, it's 0.84 meters. Yeah. Therefore, the difference in oil levels in the manometers is 0.84 meters, and we are done. Okay, next 4 problems left. 22. A pressure of 42 kilopascals is measured 2.8 meters below the surface of an unknown liquid. Determine the specific gravity of the liquid. Again, it would be nice if we can visualize this problem. So, okay, so let's say we have a container here. Alright, let me do this a bit more creatively. Okay, pressure of 42 kilopascals. Okay, so you have a liquid here at approximately 2.8 meters. There is hold on, there's a pressure of 42 kilopascals. Okay, determine the specific gravity of the fluid, of the liquid rather. Okay, this is the given. Let's just given and asked actually. Since we're asked to find the specific gravity. Okay, move on to the solution. So again, we use the initial formula, P equals density times gravity times the height, and then you can consider this again, of course, as specific gravity times the density of water, but we're looking for that, so we equate this into the equation. So we will write the equation as G P H2O, yeah, density of water H. Now what we just need to do is divide both sides by this variable right here, H2O GH, same as this, P water pH, cancel. Therefore, no space, specific gravity is equal to this, P, pressure, over the density of water times the gravity times the height. Okay, and of course, since it's 42 kPa, we convert to pascals. And again, it's just simple. I just write the value in pascals. It's 42,000 newtons per meter squared. We will do something with the variables again. Then density of water 1,000 kilograms. So yeah. Okay, times gravity 9.81 meters per second squared times the height. The height you converted, yeah, it is already converted actually. It's 2.8 meters. And now you notice, what if we try to convert this into this times meter per second squared? You notice that, look, this cancels. This cancels. Hold on. However, there are quite some blunders here that you have to look out for. Now, hold on, I'm not done yet. This unit is pascals, and you remember the equation? All of this leads to pascals or newtons per square meters, right? Very good. And finally, if you input that in the calculator, so since PGH, since this is, hold on, so you can understand it more clearly. Dito, ito ay P GH. No, this is raw. I've been making that mistake. This is raw, and that is equal to pascals. You see? Therefore, we solve for this. This is equal to 1.529 and so on. So we can say that our specific gravity, hold on, specific gravity is approximately 1.53, and we are done. Therefore, the specific gravity of the liquid is approximately 1.53. There we go. Is it okay? Now 23. Oh my god, I didn't expect this to be so tiring. Okay. 23. The average specific gravity of seawater is 1.2. Determine the absolute pressure at the bottom of 2,800 meters of sea. Okay. Similar to the last problem. Given SG of seawater is equal to 1.2, and the height, which is 1,800 meters. Okay, now you consider this. Because we will try to solve the equation here. Mention that this is the sea. Yeah, this is why it's quite similar to the other equation, right? Imagine this. The normal specific gravity. This is the SG, and the height from there up to below. Let's just say that it's approximate. It's 2,800 meters. You're looking for the absolute pressure, which is P absolute. at the depth. Okay, at the height of this height, we're looking for the absolute pressure. Okay, now for the solution. For the solution. Okay. Uh-huh. Okay. So for P absolute, the formula is the standard atmosphere, which is P sub 0, P0 plus the specific weight times the height. However, we do not have the specific weight, so we can always substitute that to the P sub 0 plus the density times the gravity times the height. Okay? Note, the standard pressure, the standard pressure is 1 atm, and 1 atm is equal to 101,325 pascals. Okay. Now to solve. Move this out. Okay, 101,325 pascals plus the density of water. No, hold on. Yeah, hold on, I missed something. This density over here is the same as, we add the specific gravity, Sg times of water, right? Because we do not have yet the density of the seawater. Alright? Yeah. So we add 1.2. Let me reconstruct this formula. P sub 0 plus specific gravity times, okay, let me just, specific gravity times the density of water times the gravity times the height. Okay, times gravity times height, meters. And now again, we take note that this is all Pascal. It leads to pascals. Okay, and then you input this in the calculator, and we will have a total of, I think this is 33 million. No. have a computer for that. Hold on. Plus yeah. It's 33 million. 62,125. Okay, Pascal. You can rewrite that as 3.306 times 10 to the 7th power Pascal. Much better if you can just compute convert that into megapascals, which we will do. So you just divide this by 1 million. Divide that by 1 million and you will have the absolute pressure to be approximately 33 megapascals. And hold on, we are done. Right, very good. Good. Alright, move on. Number 24. Okay, getting closer now. I'm recording for almost 2 hours 30 minutes. Wow. 24. A fluid with a vapor pressure of 0.102 pascals and a specific gravity of 9.65 is used as a barometer. If the fluid's column height is 1.25 meters, find its atmospheric pressure. Okay. So we're given 0.102 pascals, have the specific gravity of 9.65 and the height of 1.25 meters. We're asked for the atmospheric pressure, PATM. And for solution, we consider this, that PATM is equal to P vapor, and this is part of the formula, plus the density times the gravity times the height. And again, of course, this is just specific gravity times density of water. Yeah, density of water, just put it here. There we go. And we will rewrite the formula. P vapor plus specific gravity times H2O gravity height. Okay, and we input our values. Okay, so 0.102 pascals plus the specific gravity 9.65, density of water 1000 kilograms per cubic meter, gravity, of course you already know that, and the height, which is 1.25 meters. We input this in the calculator and we will end up with 118,033.227 pascals, which we can just convert into pascals by dividing this by 1000. Yeah, to kilopascals. Yeah, so we can say that our atmospheric pressure is approximately 118.3 kilopascals. Let me make that a little smaller. 118.3 kilopascals. That is our final answer, and we are done. Okay. Finally, okay, last problem. Number 25. The pressure gauge of a boiler reads 170 psi, which is pound per square inch. Yeah. Determine the pressure of the boiler in megapascal absolute. Take note of megapascal. Let me zoom in. Megapascal absolute. Okay. Now we consider the given. As we always do, we're given 170 psi. This is psi. Yeah. And we are asked for the pressure of the boiler in megapascals. Consider that. And for our solution, yes, okay. Absolute. This is pertaining, or actually, it's pertaining to absolute pressure. Okay. So P absolute pressure is equal to, again, we have the atmospheric pressure, PATM, and PG, I think, yeah, P gauge pressure. Yeah, gauge pressure. Now, yeah, this is pretty easy. We convert first PSI to the nearest conversion factor unit, which is kilopascals. So we write this. Let's just do it in the equation itself. So it's 14.7. No. That was for the other equation. But this is 170 pound per square inch times. Now we convert. Hold on. So that is 101.325 kilopascals over 14.7 pound per square inch. Okay? Cancel. And we consider, let me just compute it. Okay. And we still have the gauge pressure. Okay, hold on. We're still supposed to add the gauge pressure, which is the gauge pressure, by the way, is just this, you know. Okay, I think it was constant in this problem. It was not mentioned. Yeah, 101.325 kPa. Now you compute this on the calculator. That is 1273.11074 kilopascals. And to get megapascals, you just divide this by 1000. Let's just do it here since that's the last problem anyways. Let's just round it off. 0.11 kPa. MPa. Hold on. MPa over 1000 kilopascals. Cancel the units. And then we'll just round it off. So our absolute pressure is approximately 1.27 megapascal. And therefore, yeah, we are done. Again, the pressure of the boiler in megapascal absolute is approximately 1.27 megapascals. And we are done. So if you stayed till the end, well, I commend you for that. How long am I recording? 3 hours and 40 minutes. So alright, that's quite a long time. So wow, it feels surreal. It feels surreal to have completed this, even though it's just 25 problems. And there were some blunders along the way, so I hope. Well, it is actually my first time going on a long endurance run of solving this many problems at once, so yeah, it was kind of past my limit for some time, and I got some blunders along the way, but that's fine. And again, I said that I would talk in English and Tagalog, but it was like mostly 99% English and 1% Filipino. So yeah, well, I guess that pretty much wraps it up. Those are 25 chemistry and physics problems that we can encounter in college. But those were pretty basic, yeah, on that level, since we are encountering more of that here. And yeah, so if you guys found that helpful, then that's everything for me. And I don't want to keep you guys waiting for longer. And yeah, thank you guys, and bye bye.